on track to still take the test on the following Monday?
Right on schedule.
I'm already
Okay. Okay. I haven't got to look at it, but I totally like it.
I read the whole chapter.
Things like this. You're back.
Great.
I'm glad that's
Should I bring the rock?
These stupid things are all stretched out. That's why
Oh, that's it.
Yeah, I put mine on the calendar. My calendar at home. I remember to make sure before it's due.
All right, here's the cardiac cycle. The cardiac cycle is the physiology of the heart, specifically all of the mechanical events in one heartbeat. All the mechanical events of one heartbeat. One lub dup, which are the sounds you hear in the stethoscope. Okay. Yeah, the average heartbeat is 0.8. Because if you have, in one heartbeat, if it takes 0.8 seconds, you have 60 seconds in a minute. If you did that math, 60 divided by 0.8 is 75 beats per minute. That's why they give you the 0.8 as a textbook average for the cardiac cycle. Now, turns out the heart sounds are the sounds of valves closing. Valves closing make a sound, not opening. Also, what you see is that the heart has a filling phase and an emptying phase. So we call that diastole and systole. You have the atria, and you have the ventricles, or four chambers. They both cycle through a period of diastole. Another confusing thing that we have to live with. It's spelled diastole, but it's pronounced diastole and systole. So that's one thing you have to figure out. Are the atria in diastole or systole? Are the ventricles in diastole or systole? We focus on ventricular. If it's not said, it's ventricular. Okay, they're the important ventricles that are pumping the blood. Okay. The other things to keep in mind as we go through the cardiac cycle, besides diastole, systole, are the valves opening and closing. You have to keep track of the AV valves and the SL valves. And we usually focus on the left heart, not the right heart, when we teach the cardiac cycle. Although you could teach it from the right heart, usually it's left heart. And if it's left heart, it's left ventricle, left atrium. Those are the chambers we would be paying attention to. LA, LV. If it's valves, it's the bicuspid valve and the aortic SL valve. Okay, that's another thing to keep in mind. And of that 0.8 seconds, as we'll see, the heart actually spends more time in diastole, about 0.5 of that 0.8. So the rest is the heart's in systole. Okay, that's kind of how it breaks down. The heart must fill with blood before it can pump blood. And so that's why I showed you that slide right before the break. If you look at the picture on the left, when the AV valves, when they're open, the ventricles can fill. Okay? If you look at the picture on the right, when the SL valves open up, you're pumping blood into the arteries. If you look at the picture in the middle, there's a brief moment, a couple of times, where all the valves are closed and there's no inflow or outflow. Okay, but those are the three possibilities. So, how I go through the cardiac cycle is I use the pictures, I look at my bullet points there, and then I also kind of track out the data on the board that you have to know for the physiology. One last general rule that applies to all the phases when we talk about the cardiac cycle. I always want students to think about pressure gradients. Pressure always flows from an area of high pressure to lower pressure. High to low. Let me change my batteries so long. All right, it's better. And let's look at our pictures here. I chose to include these pictures because it shows valves opening and closing. I chose these pictures from the Marriott textbook. They show how blood is flowing inside the heart. These internal arrows are blood flow within the heart. And they have these black arrows, which mean systole. So if you don't see black arrows, what does that mean? Diastole. That's the only other possibility. All right. What I'll draw for you on the board, two things. Pressure and volume plotted against time, that 0.8 seconds. This bottom graph will be for volume, so we're going to use milliliters as the unit. Put some numbers up here for you. 5120. Here I'll go 0, 10, 80, 120. And the units for pressure will be millimeters of mercury. Okay, and we'll just kind of plot out what you're supposed to be seeing from the pictures. So this first phase is called inflow or ventricular filling. Now the ventricular filling, I don't know how else to describe it than saying you're filling the blood with ventricles. Okay. The ventricles are definitely in diastole. This is that 0.5 seconds where you fill. It could be early, mid, or late diastole. Early to mid to late. That's why I show the 3 pictures on the bottom. You can see that they're kind of empty early on. Then it goes to mid, then it goes to late. Books usually start at mid diastole as a starting point. Okay? It's all inflow, but that middle picture on the bottom represents mid diastole. What's happening there is the left atrial pressure looks something like this. This is pressure of the LA, the left atrium. It stays very low throughout the entire cardiac cycle. However, for inflow for the left ventricle, I use purple. For those of you that use colors, I go purple, red, orange, green. Well, anyways, so I'm going to put a line right here, purple line for mid-diastole, where you're filling the ventricles with blood during mid-diastole. I put the line lower than left atrial pressure because for pressure gradients, if blood flows into the LV, the LA pressure is a little bit higher. Okay, that's the pressure gradient rule. And as you fill, this is what it looks like on the volume graph. You're just kind of filling like that. You're increasing the volume of the ventricle. You want to fill it up as much as possible so you have a lot of blood to pump when systole comes. When you get to late diastole, of the ventricles, that's when you observe atrial systole. The atria contracting push the last 30% blood into the ventricles to top off the filling. Something like last 30% of the ventricular filling. Now, that's why I put that little blip in the left atrial pressure line. And when that occurs, it causes a little blip in the LV pressure. Okay, so I'll just put that there. And it causes a little last minute jump to finish off the ventricular filling. The volume of blood in the ventricles at the end of filling is called the end diastolic volume, or EDV for short. End diastolic volume. The volume of blood in the LV at the end of diastole. So sometimes they make it easy for students, right? Like if you say, what's the end diastolic volume? You answer, it's the volume at the end of diastole. You can kind of look at each other. What's that? I don't know. I guess you don't know what diastole is. Let's put a number to it. What's the level? 120? I don't know. That's how much you have available to pump. Okay, so then after diastole, you go into systole of the ventricles. Here. So I'm going to show you this picture here. That top picture, well, let's just name it first. I'm going to erase the notes here. This is called isovolumetric ventricular contraction. ISO. I'll write the first word, isovolumetric. Iso means same. During this phase, volume in the ventricles does not change because all the valves are closed. Ventricular contraction. Think of this as the first part of systole. All the valves are closed. So there's no inflow, there's no outflow. So whatever the volume of the blood was prior, it kind of remains. So that's like 120, just nothing coming in, nothing going out. But what you're doing is you're rising to meet arterial pressure. Pressure in LV is rising to meet aortic pressure. Aortic pressure is up here. And it's dropping to 80. Remember, average blood pressure is 120 over 80. And the reason why it's dropping during diastole is because the heart's relaxed and it's not generating any pressure. The blood is flowing away from the heart, so pressure in the vessel is dropping. But during this time, pressure is going to rise. So I'm going to use, I said I'd use red, right? So I'll go red for this phase. Pressure starts to jump up, and it's going to exceed atrial pressure. It's going to go all the way up to here. I'm going to put a little red line here to here for the volume curve, just keeping it at 120. The volume doesn't change. One point to note, as soon as pressure of the left ventricle exceeds that of left atrium, you close the bicuspid valve. So I'm going to put a star here. Bicuspid valve closes. You get the first heart sound, love. So again, notice the pictures, how it shows that. The black arrows mean systole of the ventricles. Blood wants to flow backwards into the atria, but it doesn't. Those valves, the AV valves, they both close. Okay. So here's a picture of the AV valves open and closed. When they're open, the heartstrings and papillary muscles are slack and relaxed. But during contraction, the papillary muscles contract first, and they keep those heartstrings taut so blood doesn't regurgitate backwards into the atria. So that's why you need those structures for the AV valves. They keep them closed while you're squeezing the heart. So when you identify things on an AV valve, be sure to point out that you can know the difference between the cusp, the strings, and the papillary muscle. Those three things. I kind of look for students to be very specific about that. All right, let's see. All right, that's it for isovolumetric. Now this is kind of the job of the heart here. It's called outflow or ejection. Outflow or ventricular ejection. Okay, so for this, LV pressure exceeds aortic pressure. That pressure allows blood to flow into the arteries. That's outflow. I want to draw the aortic line. It looks something like this. So this black line is aortic pressure. For the LV pressure, I'm going to use orange for outflow. It must exceed, pressure of the LV must exceed pressure of the aorta. So I'm going to continue it on as orange. I'm going to draw it slightly higher throughout the course of outflow and look something like that. LV pressure a little bit higher than the aortic pressure. That allows the valve to open and you can push blood into the artery. So at this point right here, right when you get above 80, that's the first point at which the aortic SL valve opens. Aortic SL valve opens. Notice how there's a pressure rise and a pressure drop. So muscle actually starts to relax during outflow. Okay? But you push out most of the blood first during that pressure rise and pressure peak. So it kind of looks like that. At the end of outflow, I mean, you got to figure out how much blood you've ejected. Pretty much from there to there. The volume of blood at the end of systole is called the end systolic volume. And systolic volume. But what's the number? How many mils? 50. That's why I put the 50 there, right? Because like, you don't push, it should be 0, right? No, the heart doesn't push it all out. Okay. Well, let's say you go 50, for whatever clinical reason you get tired, 55, 60, 65, 70, ESV gets higher. Is that good or bad? That's bad. Cardiac performance is doing worse. Maybe there's high blood pressure. Maybe there's a small heart attack. Made the heart weaker. But anyways, ESV, that's what it is. All right, so now when you get to here, well, let me get to the next part. Let me give you this. Stroke volume, SV. Stroke volume equals the EDV minus the ESV. Calculate that. Give me a number. 70. 70. You got it. 120 minus 50, right? That's an important number. That's how much the heart ejected. Okay. All right, so then the heart is starting to relax. And the next phase is called isovolumetric ventricular relaxation. Takes 2 breaths to say that. So relaxation tells you you're getting back to diastole now. The heart muscle's relaxing. Pressure's going to drop quite a bit. I'm going to use green for this. Pressure drops all the way back down like so. All the valves are closed. No inflow, outflow. So the volume stays the same. Whatever the ESV was, 50, doesn't change. Okay. At this point, right here, when LV pressure drops below aortic pressure, you know, blood starts to flow backwards from artery back into ventricle. But at that point, the aortic SL valve closes. Aortic SL valve closes. So what had just happened in outflow is, in the aorta, the valve was open and blood was flowing through it. They call that positive flow. But when you start to head back to diastole and pressure drops in the LV, blood starts to flow backwards. And blood accumulates in that sinus space inside the aortic SL valve. But they call that negative flow because blood is starting to flow backwards. But by flowing into that sinus space on the valve, that actually closes the valve. When the valve closes, you get this quick reversal of blood flow that restores the positive flow. But that quick reversal is shown as the dicrotic notch. That one. Right, that's the dicrotic notch, the quick reversal of blood flow. Well, anyways, when pressure drops, this is what they show for the picture. Nothing's in systole, everything's relaxed. What's that? What number is it? Yeah, it's the 50 thing. It's the systolic volume and just pressure's dropping. And, well, it drops all the way until you can start filling again. Just draw this below here. Boom. All right, so at this point, right there, that's when the bicuspid valve reopens. So we call this early diastole. It's the start of inflow again. Inflow. Early diastole. So what I had said was purple star, bicuspid, and you start filling. That's what they showed in the picture there. So you can kind of show that here. Just kind of go like that. So that, you know, that's why we started at mid diastole, because we ended there. Here's a picture of a semilunar valve from the top. So you can see how they close. You got that little seam between the cusps, but that space, blood flows into this space, and that closes the valve. Okay. Oh, I forgot. What sound does that make? For this sound here, when the SL valve closes, yeah, it's the DUP, dup. Don't go, it's lub dup, okay? If you ever have to spell it. So don't go dup lub. I won't know what you mean. I've seen students do that. I'm like, yeah, it's not close enough. What I did was, I put a lot of questions within the lecture, and I made a worksheet for you to do during lab time today, so we won't do these now, because I think it's important for you to process the information. Cool. So we'll get back to that. I want to look at another version of, well, this is the same version I've been talking about. What we drew out here on the board is called the Wigger's diagram. And we didn't do the top part because I didn't do the ECG yet. But ECG, that's Monday's lecture. So it should look familiar. If you were drawing it with me, it's kind of what we drew out there. Yeah, I just want you to know where it came from in the book. There's a blank one you can study, and do you recognize those heart pictures on the bottom? I kind of blew those up and put them throughout the different phases. And so that's an important figure to study for this next exam. Now remember, did we talk about left or right heart? Left. Well, let's take a look at right next to left. The LV generates a peak pressure of something like, it got up to 120, 130, depending on what book you're looking at. That's pretty much the high number, right? The RV, it's only getting up to 30. You guys see that? The RV generates less pressure. So here's a trick question. Which one's pumping more blood? I tricked you. Look at the data. I tricked you again.
Oh, you got me.
Look at this. There's the output right there. It's the same. The output is equal. See, that's the tricky part. Because intuitively you might think, oh, well, it's going to pump less because it's generating less pressure. Well, it's going to pump as hard as it needs to match this output. It doesn't have to pump as hard because it's only pumping blood to the lungs. What are your lungs filled with? Air. And it's easier to pump against an air medium than everywhere else where it's fluid filled. It's like blowing a balloon in the air versus underwater. Okay, it'd be harder underwater, right? Because of water pressure on the balloon. Well, anyways, that explains the difference, pressure difference, but output is equal. It has to be equal. One can't outperform the other. If that happens, you have circulation problems. For example, let's say you've had a heart attack, left heart. Left LV is weak, so it can't keep up with the right. So it's like fluid gets backed up in the lungs because it can't get back to the left heart because left heart is weak. It's called congestive heart failure. The lungs are congested. Let's say RV is weak for whatever reason. Where's blood getting get backed up? In the body, you'll see your veins bulge. Okay. Well, anyways, that's why output has to be equal. If you can't match it, you have circulation problems. Okay, don't forget that. All right, cardiac cycle. Here's another way to study the cardiac cycle. We call these PV loops. In the cardiac cycle, you can plot the volume against the pressure, not against time. That's what they do here. Pressure volume curve. Okay, you got ml, and you got pressure on the y-axis, is the left ventricle. And they have different letter points. For example, let's throw in our numbers here. Let's go 10, 80, 100. So let's go from their A to their C. I'll use purple, the same purple I used for inflow. Pressure more or less stays low, it doesn't change very much. From A to C. Now that's inflow. From A to C. Or ventricular filling. Does that make sense to you? Volume changed from 50 to 120, and the pressure didn't change very much at all. Okay, that's diastole. Then you go into systole from C to D. So we go to A there. Use black. So I'll use the same red color. This is isovolumetric ventricular contraction. Isovolumetric contraction. Did volume change? No. What's volume at C? Let me see if you can read the graph. 120. What's volume at D? It's 120, didn't change. But the pressure changed. It jumped all the way up to almost like 80. At that point, you're at arterial pressure. You could start outflow. You go from D to E to F. Get this pressure rise, it peaks at E, then it kind of starts to drop off after the outflow. So pressure changed, you got your peak and then started to drop off, and volume changed from 120 to 50, okay? And then you go from F back to A. Isovolumetric relaxation. Pressure didn't change, volume stayed at 50. The start of diastole again. Okay, you also should be able to identify the valvular events where things open and close. Like at the start, at point A. That's where you begin to have inflow. That's when the bicuspid valve first opens. you get to C, that's the start of systole. That's when that bicuspid valve closes and makes the lub sound. So then what opens at D? The valve of the aorta. Let's just go with aortic valve. Aortic valve opens. And it stays open until F when it closes. So I'm going to put F over here. F, aortic valve closes. So as you study the cardiac cycle, I want to give you one link to an animation that might help you. So the animation shows the heart events, and it kind of like follows in time the cardiac cycle. So what you could do is you could go forwards or backwards, because you have the little controls here. So what might be helpful is as you're going through, if you stop it and go forward or reverse it, see it goes frame by frame, and the animation follows. So that could be helpful. All right, back to the show here. Let me see where it was. The rest of the slides are just the questions I compiled on the worksheet. Do this for credit. You can do it today, or you could turn it in by Monday. Okay. I suggest you stay here and do it with your buddies today. If you were to finish it today, you could turn it in as a group. Okay. You have a couple of quizzes listed on your schedule. Did I talk about that yet?